Yeah, so this will be a nice little, let's see, there's 8 of us?
Yep.
All right, we're good.
That'll be faster.
Yeah, I know, it'll be much better. So this is on probability, just to kind of see how well you understand probabilities. So what's the full range of a probability value? So in red, we have 0 to positive infinity. Blue is negative infinity to positive infinity. Orange is -1 to +1. And green is 0 to 1. So we're talking about probability. What's the full range of the numbers that we could possibly have? Okay, so good. So we have a pretty good foundation. So a 0 probability is an impossible event, and a 1 is absolutely going to happen. So 0 to 1 is our full range. A lot of times we'll multiply by 100%, so we'll do it in percentages, 30% probability, 40% probability, but it's 0.4 or 0.3. That's foundational. Okay, what's the probability of rolling a 2 on a single 6-sided die? So I've got this little guy here. What's the probability of rolling a 2? Nothing tricky about this. It's 1/6 because there's 6 possibilities and there's only 1 2. And so how do we figure this out? Well, you've got the total number of probabilities in the denominator. So 6 is in the denominator, and the event you're interested in is in the numerator. And there's one of those. So one event that you're interested in divided by the total number of events. That's foundational as well. So it's the event you're interested in is the numerator, and the total number of events, total possibilities, is in the denominator. So it'd be 1/6 of a chance to roll a 2. That's if everything's equal probable. We'll talk about that in a second. What about an even number? Very good, very good. So an even number, there's 3 even numbers on here, and there's 6 total events, so it'd be 3/6 or 1/2. Now we have 2 6-sided dice. Okay. And so what are the possible outcomes when rolling 2 dice?
Simultaneously?
Yeah, so you roll it and see what, you know. Okay, so some people didn't answer. That's fine. I was like, wait a minute, what's adding up? So with 2 dice, they both go up to 6, and so you can roll. There's 12 possible outcomes, and so you can. The thing that's maybe confusing about this is that a 2 and a 4 add up to 6, but a 4 and a 2 add up to 6, and a 3 and a 3 add up to 6, but those are all counted as 6. And so here we start to think about, wait a minute, are those different? What would be the same or different about those? And so we call 1 configurations and 1 permutations. And so if you roll a 2 first and a 4 second, or 4 first and a 2 second, those would be different permutations, but yet they would all be under the configuration of 6. And so just like we did with electrons, remember we had electrons populating the p orbitals, and whether they're in the first and second, or px and py, or the py and pz, or the px and pz, those are called permutations, but yet P2, 2 electrons in the P subshell, is a configuration. And so we're starting to think about different cases of permutations and configurations, and we'll expand upon that a little bit too. Okay. Now let's bring this into chemistry. Do you know the natural abundance of carbon-13? What's the natural abundance of carbon-13? You guys from organic, you did the NMR, you saw the carbon-13 peak. Or mass spec, you see a carbon-13 peak. It's 1%. And so and we're talking about natural abundances too, all of the possibilities would add up to 1, and so this is also a probability. So the natural abundance of a carbon-13 being 1% or 0.01 is the probability. If you have a box of carbon atoms and you reach in, 1 out of 100 on average will be a carbon-13 atom. The rest of them will be carbon-12s. Okay, that's if you're just going to say, to 1 decimal place or to one significant figure in the ones place. But if you went out to, say, parts per thousand or so on, you might have a carbon-14 in there, right? And so they've got different kinds of probabilities. But if you were just to go to the ones place, then it'd be 1 carbon-13 atom and 99 carbon-12s. And so what is a rough estimate of the probability of a benzene molecule containing 1 carbon-13? And so this is testing your knowledge. We haven't covered this yet. I want to see how you think through it. How many carbon atoms do you have? 6. And so now you're reaching into the bag and you're pulling out 6 atoms. Okay? So you have 6 chances to pull a carbon-13. So you have a 1% chance on the first one, and then you get to try again, another 1% chance, and another 1% chance. So you have 6 chances, or 6%. This is possible. It's a rough estimate of having 1 carbon-13 in the benzene. Now notice one of these other options was 0.1 raised to the 6th power. Okay? So now we have a bigger bag with a lot more atoms, and so there's not just 1 carbon-13 in there. In fact, we could have a mole of carbon in there. And so we could have lots of possibilities of pulling a carbon-13 out. And if we reach in and we pull a carbon-13 out, that's 1% chance. What about pulling a second carbon-13 out? Now you've got 1% and another 1%. That's pretty rare. In fact, those probabilities would be multiplied by each other. So the and or functions are logic, Boolean functions, and or. So if it's or, then it's added to like 1% plus 1% plus 1%. So if it was saying, now pull the first carbon atom out and it's a carbon-13, what's the chance of pulling the second one and third one and so on? If it doesn't matter which atom or which time I pull it out, then it's an or function. It could be the first atom or the second or the third or the fourth or the fifth or the sixth. And so when you're using the or function, when it doesn't matter which order, then you just add those probabilities. So each one is 1%, so it's 1% plus 1% plus 1% plus 1%. So I pull 6 atoms out. If I don't care which time I pull the carbon-13 out, I have a 6% chance. Okay. But if I want to pull a carbon-13 out every time, then it's the and function. So the first atom, I want carbon-13 and the second, and the third, and the fourth, and the fifth, and the sixth. Then that's multiplicative. So then they're multiplied by each other, and so I have 1.01, that's the 1%, raised to the 6th power, because I'm getting all carbon-13s out, for all 6 atoms. And so that's when you would use that 0.01 raised to the 6th power, or 10 to the negative 12 would be the result. So it's pretty rare to get a benzene, just naturally, to pull a benzene atom out of a bag of carbon atoms with all 6 atoms carbon-13. 10 to the minus 12 probability. But you think about how many molecules you could pull out of a bag when you had a mole of carbon atoms and a mole of hydrogen atoms. How many do you have? You have 10 to the 23rd. So 10 to the minus 12th probability is not impossible when you have 10 to the 23rd atoms. So if you've got a mole of benzene, 10 to the 23rd benzenes, there may be one molecule in there that's pure carbon-13 all the way around. It's kind of weird to think about. Even though it's a low probability, it's not impossible. Okay, you get down to like 10 to the minus 70 and so on, those numbers, then you're talking about impossibilities. But 10 to the minus 12, very, very, it'd be impossible to detect, I'll say that. Okay, but not necessarily impossible to happen. Okay, so let's see what we got. Good job. Oh, we got animations here. Now, they've drawn this out. It's kind of like the Mario Kart. I like that. Yay. Wow. They've really gone all out with this. All right, so let's get into the actual technical parts of the probability. Okay, we can turn the music off now. So let's talk about the probability. Let's use this. You know that there's really three types of probability. We've been talking about empirical probability collecting data, but we also used logic. We used or and functions, and so we have the logical probability, and so these are just some definitions. These will not necessarily be tested. I'm just giving you background information on probability this morning for this lecture. And so logical probabilities deal with rational decision making. You know, if you have some evidence and then you make a decision based upon that evidence, and you're typically using probabilities and logic. And so there's logical probabilities, empirical, where you have a mathematical description of measurable parameters. Okay, like the carbon-13, we have a 1% chance of carbon-13 in nature, and so we can do empirical measurements and see if this benzene molecule follows those probabilities. So there'll be an empirical test. You know, this is actually what we do to determine if something is a meteorite or not. Because we have the natural abundance, the periodic table, those are the average atomic masses for Earth. And so if we have a rock and it's got an iron, core to it, and we test the isotopes of iron and nickel and so on, and it doesn't match the relative abundances on Earth, and we know this didn't come from Earth. And again, we're using the probabilities of the abundances of those atoms, those different types of isotopes, to determine whether this is a terrestrial object or not. And so, we found benzene in a comet, okay, and it was all C13. You're like, whoa, that's crazy. So this came from a place where C13 is not just 1%, because the probability of getting a pure C13 benzene molecule is 10 to the minus 12, and here it's 0.5% in this particular object. So that would be very interesting. And so then it requires, of course, this empirical requires a foundation of logical probability theory, but we will pull the mathematics of measurable parameters and come up with a probability in empirical probabilities. And then we have subjective, which is an individual degree of belief. So let's put all of these into perspective together and as it relates to decision making. And so in science, we make decisions. In our lives, we make decisions. And so we use the subjective all of the time in making our decisions. Like you say, well, for me, I want to do this, or for me, I want to do that. And so we use our subjective, personal perspective to make a decision. And we sometimes will find data and cherry pick data to make ourselves, comfortable with that. But this is all three of these are all wrapped together. And so let's look at this. Probability and decision making. So we have a subjective, uninformed opinion, right? We just decide, hey, this is the decision I want to make. And so we make our decision using our subjective, uninformed opinion. And that's kind of risky. Sometimes you get lucky, right? You make a good decision, and it was just because you had a hunch. You just decided to go here, okay? We like to get away from those things in science and in business and in, all endeavors. And so what we'll typically do is we'll try to make a logical or rational or evidence-based decision, but without data, it's still kind of a subjective, uninformed opinion with some logic thrown on top. Okay, but it's a little better. At least you're trying to argue. You're making an argument for your case. And so you may have heard this movement towards data-driven decision-making. We want to use empirical evidence. And so we'll go collect data. We'll measure some things. And then from that data, we'll use logical, rational, evidence-based. If we want a certain outcome, we'll measure data and see which outcome is more favorable to whatever goal we have, and then we'll make a decision based upon that. And so that's what the green path is. But notice we're still using logical or rational decision-making on top of our data. The data doesn't tell us what to do. We have to compare the data to our goals. And once we compare the data to our goals, then we can make an informed decision. And you do this enough, eventually you realize the data is pretty stable, and we don't need to go back and constantly collect the data. We know the system. And so that's when you become an expert. And so you have an informed expert opinion, and you've collected data long enough. And collecting data doesn't have to use lab tools. You can just observe. You could observe the way the world works, and you're like, okay, I've seen the way the world works, and now I have an informed opinion, and I can make decisions based upon that. But notice how it's slightly yellow, because if the world changes, if the data is different, if the experiment's different, then your informed expert opinion, the experts in quotes, you may not know the current situation if you don't constantly check yourself. And so these are the three different types of logical probability tools. You have empirical, logical, and subjective. Subjective without any data is uninformed. Subjective with data and with logic is informed. And you just always need to check yourself against the way the world works. So this is sort of a way to kind of capture all three probabilities. And the most important usage of those things is making decisions. Notice too, this is a philosophical side note, that without the ability to have free will, and there's a lot of scientists and philosophers and so on now saying we don't have free will, none of this works, right? Because you can't make a decision unless you're free to make a decision. So collecting data, you have to decide what data to collect. Collecting data, you have to decide whether the results are valid or not. You have to evaluate the evidence and then make a decision. None of this works without free will. So that's the mini lecture on philosophy. None of this works. Science doesn't work without free will. So we'll move on, because this isn't a philosophy class, this is a PChem class. So let's focus on the empirical measurement systems. And so this is where we have those events measured and the total number of events. And this is an underlying foundation for probability, is this idea of equal probability. Equal probable events can be hard to prove. So, how would I know if this dice was loaded or not? What I mean by loaded is a lot of times they'll take the 1 or the 5 or what have you, and they'll drill out the little dot and they'll put lead in there. And so one side of the die is heavier than the other 5. And so the low energy configuration for that die is for the leaded portion to be down. And so if I drilled out the middle of the 3 and put lead there and then painted it white, you wouldn't be able to tell. Okay? And I've got a mill at home, I could do this very accurately. And so I could drill that out, put lead in there, fishing weight, cram it in there, maybe melt it, pour it in, and then paint it white, and you wouldn't be able to tell. And you would be thinking that all 6 sides were equal probable, and you would be wrong. How would you know you were wrong? You have to test it. But you test it with the null hypothesis that all sides are equal probable, and then you see if that hypothesis fails. And if you kept seeing 4 come up more than 1/6 of the time, then you would come to the conclusion that the null hypothesis has failed. That the alternative hypothesis is that they're not equal probable, would be one that you would accept. And so we in our little atoms in a bag, that you're reaching in there and it's all stirred up, and that the carbon-13s are not all at the bottom. Okay, so again, it would be equal probable of pulling out all of those. There was no preference in it. So this is one of the foundational assumptions of probability theory, is that you have the law of insufficient reason. You have an insufficient reason to believe there's any preference to the outcomes. And so this law, or principle of insufficient reason, specifies the probabilities of 2 events will be equal if there's insufficient reason to believe the probabilities will be different. Notice how it's a statement. It specifies that they will be equal. So they're saying that the probability of getting a 1 or a 2 or a 3 are all equal in an unloaded die. Okay. And sometimes this is attacked because it sets too many probabilities to be equal. Okay. But it is the null hypothesis. You have to do statistical testing to see if that hypothesis is rejected. So the objects under study are not single events, but sequences of events. And so we have to go through and determine if there are trends in the empirical probabilities. And these emerge as the sample size increases, and they typically will be, you don't get a single number, you get a distribution of results. And there are lots of distributions. Which one of these distributions are we familiar with mostly?
Gaussian.
The Gaussian distribution, yeah. And so that's your normal distribution. All of our, almost all of our peak shapes in spectroscopy were Gaussian because you had a particular transition plus random variations. And random variations could be in the spectrometer, like the source or the detector, or it could be in the motions of the molecules, random motions of the molecules. So there's a lot of random events, just normal random events will give you a Gaussian distribution. But there are other kinds of distributions, like the Poisson distribution is what you get from radioactive decay. And so counts per minute, anytime you have counts per minute or you know, anything per something else, a lot of times your evidence versus time, your sample versus time, would give you a Poisson distribution. And randomness, this is an important point. Randomness is the absence of a trend. So it's hard to prove that something's random. You have to prove that it's not random by observing a trend. So if you don't observe a trend, then you're saying the process is random, but you haven't tested for randomness. You've not observed a trend. It doesn't mean there's not a trend in there, you just didn't detect it. So randomness is a baseline assumption. If you fail to detect a trend, then you just result to your baseline assumption, but you're assuming that it's random. You haven't tested whether it's random or not. Okay. And so this is what we just determined in our Kahoot. The first law of probability is that your event is between 0 and 1, including those, but rarely including those. A sure event is 1, and an impossibility is 0. The second law is the Boolean option, or Boolean logic of the OR function. So mutually exclusive events, meaning like the carbon-13 thing, it's either, if we have one carbon-13, it's either on the first atom or the second or the third. Notice how that's mutually exclusive. If it's on the third, it's not on the first. So the mutually exclusive events is equal to the sum of their individual probabilities. So I have 6 positions and I have 1% for each position. So I have the sum of those. So it's about 6% for the carbon. Notice this is, I keep saying it's about 6% and that's close because I'm only assuming that I have one carbon-13. It's mutually exclusive to have 2 carbon-13s. So there is a possibility of having a carbon-13 on 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6. And so those need to be figured into the denominator as well. So it's a slightly less than 6% chance. But anyway, if you have the probability of event 1 or event 2, that's equal to the sum of the probabilities of event 1 plus event 2. Okay. So then let's go to the second one. If you sum up all the probabilities of all the individual events, then they add to 1. So that's normalization. So we've seen normalization before. We saw that in the probability distribution for the Schrodinger equation. You know, we're looking at the wave functions and wanting to normalize those, and it was the wave function squared was the probability distribution, and if we sum that over all space, then we've got all of the probabilities, and we set that to 1, and we call that normalization. It was really a logical probability exercise that we were engaged in when we were normalizing our wave functions. Then the third law, this and that, so we have 2 events that occur together, like drawing an ace of spades. Notice we're drawing an ace, which is 1/13. There's 13 types of cards in there in terms of 2, 3, 4, all the way up to ace. And then we're also spades. So 1/4 of the cards are spades. And so we have the probability of an ace, 1/13, times the probability of spades, 1/4. And so those are multiplied by each other. So that's the way we write that. Over on the left, you see the probability of ace, vertical line, spades. We're saying, what's the probability of an ace given that I drew a spade? Okay. And so it's the probability of ace, which is, again, 1/13 or 4/52. And then probability of spades, which is 1/4 or 13/52. So it would be 1/52. Now let's bring this to more of a, I'd say, general mathematical principle and talk about expectation values. Because essentially we're talking about that with cards. What's the expectation of drawing an ace of spades, right? Well, in chemistry, we're saying what's the probability of a molecule being in this energy level, right? So that's what we want to think about in terms of thermodynamics. What's the population of our energy systems? And so here we have these values of distributions. Notice the angle brackets, and we kind of did this in the fall with quantum mechanics. We would say, you know, what's the expected energy? If I have a set of molecules in a system and I pulled one out, what's the expected energy? And so that's the expectation value. And these are the functions. It's the sum of all the probable states and the value associated with those states. So if we're dealing with energy, we have the energy of each of the states, and then we have the probability of being in each one of those states. So it's the sum product. We have the energy times those functions. And so here's the value function. Most of the time we're talking about energy. Okay. And then we have the probability function. Notice there's two summations. The summation in the denominator is the normalization piece. That's the all possible events. Okay. And the piece in the top is the individual event you're interested in. So that's the probabilities. The event you're interested in divided by the total number of possible events. And then that's your probability piece in green. And that probability may be a particular value like energy. Let's do an example. I know you're kind of writing these equations down, but they are in the notes, and there's a lecture online so you can capture it later. So let's look at a carnival example. You go up to the carnival guy and he says, hey, pay $1.50 to throw a dart, but look here, you could win $5 if you get it in the red zone. You could win $2 if you get it in the blue. So it looks pretty big. You're looking at this, you're making a subjective evaluation, and you're thinking, I'm pretty good. I could hit that red one. I give him $1.50 and I throw the dart, and I have a pretty good chance of getting $5. Maybe I'll get blue and get $2. Either way, I'm ahead, right? But it turns out you're not as good as you think. And in fact, you can hit the green every time. You know, this big circle, you can hit in there every time. But as far as aiming any better than that, you have an equiprobable chance of hitting anywhere inside the biggest circle. Okay, so sometimes you're going to hit the red, sometimes you're going to hit the blue, most of the time you're going to hit the green. And let's just look at this. So we'll say the probability of hitting one of those places is just based on the area of them. And so notice we have a radius for the red, twice that radius for the blue, 3 times that radius for the green. So we know the areas of these, so we know the probabilities. So the math over here on the right is just looking at the areas. Pi r squared for the area of the red, okay? And the area of the blue is 2r, okay? So it's 4 pi r squared, because r squared, right? Is the area of the blue, but we got to subtract the area of the red. So we subtract that piece that's the red, the pi r squared. So we have 3 times the area of the red is the blue. Okay, does everybody follow that? And then again, the 9 pi r squared is the area, the total area of the green, but we got to subtract the area of the blue, which contains the red. So we subtract 4 pi r squared for that, and it's 5 times the area of the red is the green. So all of these essentially are based on the area of the red. So what's the probability of hitting that red? It's the area of the red over the area of the red plus the blue plus the green. All possible events. Okay, like I said, you're good enough to get it on the dartboard at least. So we're not talking about a total miss, okay? And so that's 1/9 for the probability of getting in the green, of getting in the red, 3/9 for hitting the blue, and 5/9 for hitting the green. So the probabilities don't look so great. I mean, 5 out of 9 times you're going to hit the green and get 0, but you paid $1.20, $1.50 to throw the dart. But notice how those are probabilities. They don't tell us what we really want to know. Well, what do we really want to know? We want to know about money. So the value function is the money. And so related to our example, the value function is going to be energy, but the probability function may be based on area. So the probability can be based on something totally different than your value function. I guess that's the mental piece that I want you to take home. So the value function in this example is money. So it's 1/9 chance of getting the $5, Everybody follow that? 1/9 is the chance of hitting a red, and the value function for that is $5. And it's 3/9 chance of hitting the blue, and the value function for that is $2. And then the 5/9 chance of hitting the green, and you get 0 money for that. You add all of those up, and you get the expectation value for money. So the angle bracket, $sign, that's the expectation value of playing this game, and it's $1.22. So if you played enough times, your winnings would average out the expectation value of $1.22. And so that's why the carnival guy charges $1.50. Okay, because he knows on average over a whole day or a whole week of carnival time, he's going to make some money. He's going to make what, 25, 67, 27 cents per game. But hey, you know, over a whole week, it's enough if he gets enough plays. And so that's why it's always annoying people that walk by. Hey, come throw the dart. You look pretty good at darts. You're coming over here. You can throw the dart and get $5. Look at that. Look how big that red square is, you know. And he can pull you in, and you can pay. Because again, and then you make a subjective decision that $1.50, that's not worth that much, you know. It'd be worth the fun of throwing the darts. And so you make a subjective evaluation to try the game. Now, if you throw it and you hit the red, walk away. Take the money and go. Because the expectation value is $1.22. So the more you play, the more you're going to lose. So this is your principle for Vegas. If you're going to go to Vegas, you know, as soon as you get up, walk away. You know, it's going to go down, and you're going to reach that expectation value where you're losing money. And you could do the same thing with energy. Instead of dollars, 5 joules, 2 joules, 0 joules, and so on, and you could get, you know, 1.22 joules out of this, if joules was money. Okay. Now we can do continuous expectation values with the same math. Only instead of discrete sums, where we can add up the areas, right? We can have functions, and they can be smooth. Like we had red, and then it jumped to blue abruptly, and then it jumped to green abruptly. But it doesn't have to be abrupt. It could be a function. It could be a smooth function. In which case you just have sums. You have integrals. Okay, but it's the same math. Instead of a discrete sum, you have an integral. Okay, and that's what, you know. That's why you took calculus, right? And also why I taught you Excel. You can just put that function into Excel and solve it up, and the greater number of rows, the more infinitesimal there is, and the differences between those rows, and then you get better results. And so this is again the value function and the probability pieces. So now we have integrals instead of sums, discrete sums. And so there's the problems with these empirical probabilities, and we'll end with this. These experimental results, these are empirical probabilities. These are descriptive statistics. And now this is added. This isn't in your notes because I didn't want to lose my thunder here. So descriptive statistics describe things. So large sample sizes give you a confident description, but they're expensive. Okay, so there's this pull in both directions. You want to have a good trend, but it costs money to do that sample. Okay, to do that experiment. Descriptive statistics show correlation, that these two events have a trend between them. That there's somehow a trend, but they don't give you causation. Event 1 causes event 2. And descriptive statistics are not explanatory. They just describe the trends. They don't explain them. That's where your mind comes in as a scientist, trying to figure out how event 1 is related to event 2. And in fact, an explanation in chemistry many times is a reaction explanation. It is a mechanism. Notice you can still do good chemistry without a mechanism. You can put this molecule in a pot with that molecule and heat it up and reflex for 2 hours and get your results, even if you have no idea how the bonds are made or broken, right? You can be a really good chemist without a mechanism. And you could just have that data. When I use these percentages and so on, I get these results. And they're correlated, but you don't know what the cause is. You don't know how that bonds are broken and how the bonds are made. Okay, that would be that would be causation. You know, I know that this molecule is active by this catalyst, and this is where it attacks, and so on. And so unless you have a mechanism, or in pharmaceuticals we call that a mode of action, unless you know how this drug interacts with this enzyme to cause this effect, then you don't really have causation, you just have correlation. And so always be aware of that. In fact, let's emphasize that. I've kind of talked about this, so a small class, we'll just jump right in. These are spurious correlations. This is a great site, Tyler Vigen, all one word, TYLERVIGEN.com. It's definitely worth going to visit this site. And these are spurious correlations that I pulled off of that site. And it's, again, to hammer home this idea that correlation is not causation. Okay, so here's a correlation that has 99.79% correlated. And it's U.S. spending on science and space technology and suicides by hanging, strangulation, and suffocation. Those are the two data sets. And they go up together, and it's 99% correlation. So when one goes up, the other goes up, and when one goes down, the other goes down, and it's 99% of the scatter is the same. Okay, but are we saying that spending on space causes suicide? No, we're not. Okay, here's another one. Apple iPhone sales and people who die by falling down the stairs. Now this one might actually be causation, you know, walking down and down they go, you know. But you can't make that conclusion from the data. That's a hypothesis, and then you need to go get observational science, okay? This is just showing the correlation, not the causation. You have no proof that people are falling down the stairs because they're looking at their phones. You just have that the data is correlated. You do not have a causational attachment. So again, what should be done by this, you know? Should we ban iPhone sales because people are dying, you know? So you hear this all the time. You take a correlative event or correlation and you make policy based upon that. And that's a problem, okay? You need to back away for a second and pause and say, maybe nothing needs to be done. Maybe we need to study this. Maybe we need to observe, you know? So this is descriptive statistics. It's saying these are correlated, but does one cause the other? You need more information. You don't have a mechanism yet. Okay, you just have a correlation. Here's another one. Works of visual art copyrighted in the U.S. and females in New York who slipped or tripped to their death. Okay, 93% correlated. So it's just crazy. Now I want to talk about this terminology moments. The first moment, second moment, third moment. I put this in to talk about the expectation value. That's what we call the first moment, just so that you have this vocabulary word in your arsenal. Notice how the x value in this equation is just x to the first power. So that's why we call it the first moment here. And so we're looking at the probability of pulling x out of the hat, if you will. We have the probability functions here, the f of x, and then we just take that x-axis and multiply by that probability function in some overall space. That's the first moment. What about x squared? That would be the second moment. The third moment is x cubed. What about the fifth moment? It would be x to the fifth. Okay. If these were energies, it would be energy squared, energy cubed, energy to the fifth power. Those would be the expectation values for energy squared or energy. Most of the time we don't really care about energy squared. We're talking about energy. But notice in this definition of variance, okay, of these functions, it's the second moment minus the first moment squared. And so there are times when you want to do the second moment or the energy squared term. If you were wanting to know the uncertainty or the variance in a particular energy, you get the energy for the system. What's the plus or minus? Right? That's the standard deviation or the square root of the variance. And so here's an equation for the variance. And notice this definition doesn't depend upon the definition of the distribution. This is valid for a Poisson. This is valid for a Gaussian. This is valid for no distribution, just an unknown distribution of data. you could calculate discretely what the first moment and the second moment are, and you could calculate the standard deviation of a large data set. So this is a very useful equation, and it uses the second moment. I also put this in the course just because when I was in industry, I had my bachelor's degree, I had my PhD, I went into industry, and I was reading papers on particle size distributions, and it was using these terms of the third moment and the second moment and so on. And I went back through my notes, that was never in my undergraduate career. I mean, I used those functions, but those terminologies weren't applied to them. And so I want to make sure I put that in the notes, just because I had a blind spot after I got out. That's it for today. We just did the probability. Again, the Gaussian portion, the Boltzmann distribution, is online. I really want you to catch up with that lecture. Watch the lecture on the Boltzmann distribution so that we're back on track.